Hello and welcome back. Today we're going to talk about linked lists. Linked lists, which I've kind of insinuated we were going to talk about for a while, are a pretty simple data structure to conceptualize, so we're not going to go through the code. I'm not going to type along for this one. We'll just look at the code because frankly, they're not very long functions for this, and it makes no sense to retype them. Let's just dive right into it then. All right, so we'll start with the node class that I have on the right here, which is what linked lists are composed of. And feel free to read the comments, but I'm going to be going into more detail on this stuff than the comments do, so don't worry about it. All right, a linked list is basically a series of these nodes, and a node contains at least, let's move this around so it's not too unclear, at least these two pieces of information. And they have, at the very least, a payload, so whatever the data is that you're trying to store, and then a pointer. You've probably heard that word before, but maybe we haven't gone into what it means. A pointer to the next node. So what is a pointer? Well, in Java, we don't really deal with pointers directly. In other lower level languages like C, you have a concept of pointers where you can actually, instead of accessing a variable, you can access its pointer. In Java, we like to kind of think about all variables by their pointer. And then let me give you a quick example here. If you have a public int add1 function, and you take an int n as an argument, and you return n plus 1, what is this n, really? Is it the value that you passed into it? Or is it a reference to the value that you passed into it? Well, that's a weird question, right? Well, let's say that you passed 2 into this function, or a variable with the value of 2. You expect this n to equal 2 when it evaluates, and you expect it to evaluate to 3. But you also expect that the n that you passed into this function, the one that came into here as input. So if you called this function as like add1 x, and x was your input into the function, you would expect that x would not be modified. You would expect that x would still be equal to 2 at the end of this execution. So this would be like new x, and they would be equal to add1 of x. But you wouldn't expect x to have changed. If x changed, that would be pretty weird. So what you're passing into this function is the value. You're not passing the reference to x. If you pass the reference to x, then it would change when n plus 1 occurred. And Java's a little bit fast and loose with when you're passing a reference and when you're passing a value. And you might find it's surprising that you've probably developed an intuition for when a reference and when a value are being addressed. So going back to what is a pointer, what does it mean to say node next here? This is a, let's call it a hint to the location of the next node. This is the location of the next node in memory. It's not actually the value of the next node. It's not its containing data or everything, but it does tell you how to reach it. And so if I called this node's next value, I would be able to get the next node, and I would be able to look at its data and all of that stuff. And the other thing that might be weird about this is that we're inside the node class, and yet here we have a reference to another node. That might be a little bit unusual. We did this with the recursive example too. We generated different recursive art structures. We generated circles or whatever, and then they had a reference to a circle that belonged to them, and then they had a reference to a circle that belonged to them, a child, essentially. And this is the same kind of relationship. You can think of the next node as maybe the child of this node, or you can think of it as the parent, and however you want to do it. We'll go back into more like parent-child relationships when we talk about trees. When we talk about linked lists, we're usually thinking of next and previous as more like the node to the right and the node to the left. So if I was to write, let's say, a sentence, so let's say I have string words equals the quick brown fox jumped over the lazy dog. If I was to write for you a sentence like that, and I asked you, for the word quick, what is the next and what is the previous word? You would be pretty easily able to tell me that brown is the next word and the is the previous word. And likewise, if I asked you for jumped, and I said, what is the next word? You would say over. And if I asked you what's the previous word, you would say previous. And you can also do more complex operations on a sentence like this. If I ask you, for example, for jumped, what is the next word's previous word? Well, first of all, that's kind of complicated to think about, but let me say it again. If I ask you for jumped, what is the next word's previous word? Well, okay, the next word is over. What is over's previous word? Well, it's jumped. So I actually get back to jumped that way. And let's say I want to insert the word happy into this sentence, and I want to insert it right here. I want to insert it after the, so I want to say it. The quick brown fox jumped over the happy lazy dog. Well, for me to complete that operation, the concept of what's next for the and what's previous for lazy has to update. Right now, the word that's next for the is lazy, and the word that's previous for lazy is the. So what changes when I add happy is that the next word for the becomes happy, and the previous word for lazy becomes happy. As well, we also update the status of happy itself. The previous word for happy is now the, and the next word for happy is now lazy. So if you think about it that way, it should make a little bit more sense that nodes can address themselves. And they do this in the same way. And representing a sentence is actually one possible application of a linked list where each of the different nodes stores a word in a sentence. Sometimes linked lists are used for something like the undo functionality in in Notepad or something. Although not so much anymore. But anyway, okay, let's look at this in a little bit more detail. We've got our payload, the color. So each of these nodes is going to have a color. This allows them to be displayed. Again, we're going to have a visual component to this. And this is also the same as your homework starter for this week, with a little bit of extra that you won't need for the assignment maybe. And then you've got your previous node as well. This is actually optional for a linked list. So if your linked list only has the next node, so if it only has a connection to the next, then we call this a singly linked list. If it also has a connection to the previous node, then we call it a doubly linked list. You might want to ask, well, why would we even make a singly linked one when a doubly linked one only requires this one additional reference? And to that you might be right most of the time. A doubly linked list does take up a little bit more memory, though. We have that one extra reference. So whatever we get in simplicity, we trade off for a little bit of extra memory. But we're going to stick with doubly linked lists because all of the operations are just a little bit easier. They're very similar between singly and doubly linked for most things like inserting and deleting, but everything's just going to be a little bit different and a little bit more complicated. So we're going to stick with doubly for now, but keep in mind that if we deleted the reference to the previous node, we only had them connected to the next, then that would be a singly linked list. Okay, so moving on with our doubly linked list, we also have this node display, which we're not going to go into. That just allows them to be drawn to the screen, so it's not really part of the linked list functionality or anything. It's just part of the demo and the display and everything. How might you create a node then? So the most basic way to create a node, we'll start with this, is to create one that has no connections. It's just the node, and it doesn't have a connection to any other nodes yet. And the very first node that's in the linked list is always going to be created like this. It's going to be a node that has data, but it's not connected to anything yet because there's nothing else to be connected to. And now we're actually going to move right into what the linked list is organized like. Because nodes are just the units that comprise the linked list. Generally, when we create a linked list, we have two classes. We have our linked list class, which actually stores that data structure, and then we have the individual nodes. These are just the units of the data structure. This is a little bit unusual because for arrays, for array lists, for stacks, for queues, so far we looked at, they were just storing the item directly. They were storing the data directly. So why do we need the node class? Well, really the only reason that we usually have the node class is so that in addition to the data, the payload, the color, the item, the number, whatever it is that we're storing, we also have an easy place to access these next. and potentially previous pointers. So that's really the only reason that linked lists store nodes instead of storing like the color or the item or the number directly. It's so that we can have a simple place to wrap all the functions that involve that next and previous and access them in an easy way. So a node, you can think of it as data plus a couple of pointers to the next and the previous item. All right, the first item in the linked list is always called the head. So this is going to be the very first node at the beginning of the linked list. And when you start your list, it's going to look like this. And it's just the head hanging out by itself. And some implementations of linked lists also track the tail, which is the last item in the linked list. And when you start the list, obviously the head and the tail are going to be the same one. They're in the same spot. So at this point, this is both the head and the tail, because it is the only item in the linked list when we initialize it. You'll notice that when I initialize this linked list, it actually creates no nodes. The head and the tail are both null. That's your pretty common implementation. You might also support functionality to create it providing the head. Again, same thing. Note that the head and the tail are both set to n. That node that you pass in becomes both the head and the tail in a single item linked list. And let's see. Yes, that's good enough for us to get started with the display, I think. So if I run this application, it starts with a blank one of these. And the first square that I click, these add to the list. So if I click this one, I start with just this guy here, and he's got nothing else in there. It's otherwise blank list. So this is both the head and the tail. With that, let's move on to how do we add things to the linked list? How do we add additional items? This also brings us to the biggest advantage of linked lists and why they're so easy for implementing a queue. So we'll look at two simple additions first, but before we look at the simple additions, we're going to look at the special case of what happens if the list is empty. And to look at that, we're going to also look at a couple of the possible constructors for a node that don't involve providing just the color or just the payload and then set the other links to null. So we might create a node in a different way too. We might create a node and we might set its next and its previous, like so. So we might provide the next and the previous link in the constructor. And then we also might create a node and only set one of those. And if we only set one of those, we could just do something like this. We could just say new node. It would have some color, and then it would have whatever node is going to be the previous, and then null. Or if we were only setting the next and we weren't setting the previous, it could be something like this. So we could just use this implementation that we already have in order to pull that off. Or we can write a little utility like this where it's takes a boolean, and if the boolean's true, it sets the next one, otherwise it sets the previous one. I find this to be perfectly fine. Just set the one that you don't want to null. Perfectly good. So just keep in mind that there's these other two constructors that we might utilize if we wanted to. Alright, but insert if empty takes a node as an argument, and we're going to assume that it's a node like this. It doesn't have any links yet, and we need to decide what's going to happen to those links as it's inserted. So we're going to assume that all the nodes that we insert to the list are like this. They're nodes with no connection. We need to build all of the connections to properly insert them into the list. And this is usually the case. Okay, so your node being inserted into a linked list, this is pretty straightforward. First you want to check that the list is actually empty. So to check if it's actually empty, you want to see if the head is null. If it's not null, then the list isn't actually empty, and we're going to return false. This was not properly inserted, so we're going to return false to indicate that no insertion occurred. Otherwise, same as in this constructor, the new node is now the head. It's also the tail because it's the only item in the list, and we'll return true. So pretty straightforward, shouldn't be any issues there. We are inserting into an empty list. If it's not empty, we return false. If it is empty, it's now the head and the tail, and we're done. All right, that brings us to the first of our real insertion functions, which is inserting at the tail. So if the linked list is empty, we still want to return. That's why I wrote this helpful utility function. A lot of the time when you see samples of linked lists and stuff on the internet, you'll see them bake this whole check there into the front of every single one of their insertion functions. They're going to look at the if the thing is blah, blah. I like to make it a function so that it's very straightforward, but anytime you insert at the head or the tail, you have to handle that special case of if it's empty, because that's the only situation where you have to do this, where both the head and the tail are sent to the new node. Alright, so assuming that it's non-empty, that there's at least one item in the list already, what has to happen? Okay, well, this is the only item in the list at the moment, and it is both the head and it is also the tail. And it has a link going this way, that's its link to the next, and it has a link going that way, it's its link to the previous. And both of these are currently null, because there's nothing. You can always imagine a linked list as having an imaginary null node after the tail and before the head. So if we're inserting at the tail, we want to insert at the end here, then what has to happen is that this link now has to point to the new guy. We'll call the new guy 1. And then 1's pointer still points to the imaginary null at the end. Now the new guy becomes the new tail as well, so we have to update that too. The old node remains the head. So altogether, what had to update? Well, this arrow had to update. This arrow represents the next pointer for the original node, the node that was the tail before we finished this operation. We also had to update something that's not visibly shown here yet, and that's the previous pointer for item number 1. So linked lists are often represented like this, with the little carrots going in either direction to show that they're doubly linked. So this is 1's previous pointer, and this is 0's next pointer, and they're kind of visually drawn together. Alright, so we have to update this next pointer from 0 to 1, and we also have to update this previous pointer from 1 to 0, and then 1's next pointer is still null. Alright, so altogether that means that the tail's next pointer is the new guy. That handles this business right there. In fact, let me move this down so we can follow along in place. So the tail's, that is 0's next pointer, this guy, is now 1. The new guy's previous pointer, that is to say this guy, is now the old tail. Remember, 0 was the tail before we did this. And then, of course, 1 is now the new tail. And that's the last step here. And that's all we needed to do to insert at the tail. Inserting at the head is equally straightforward. We'll skip over remove at tail for now and go to insert at head. So to insert at the head, let's say that we want to insert 2 here. Well, first of all, 2 is going to become the new head at the end of this insertion. It's now in the front, right? And a couple of things have to update besides that. A lot of formatting today, my bad. Alright, a couple of things need to change besides that. First of all, 2's previous, still null, that's straightforward. 2's next is 0, the old head. 0's previous, instead of being null, as it was before, is now 2. So, altogether, head.previous equals n. Remember, 0, the old head, its previous, the new guy, 2. n.next equals head, so the new guy, 2. Its next pointer is now 0, the old head. And the new head is now n, so 2 is now the head. You'll note that no matter how many nodes there are in the list, so even if there's like a million other nodes in between here and there, right, even if it's like that, it's still O of 1 to insert at the tail and at the head. That's why linked lists are great for implementing a queue, because remember how hard you had to work to get that circular array queue working? Well, this is already a functional queue. You can insert at the head, and with the addition of the function we're about to look at, you can remove at the tail. So before we look at inserting into the middle, let's look at removing at the tail and the head, and then we'll go back to insertion into different places. But I guess before we even do that, let's look at what adding to the head versus adding to the tail looks like. So I have it adding currently to the tail whenever we press the left click on one of the buttons up top. So let's take a look at what that looks like. So here's cyan, here's blue, here's purple, here's green, here's yellow, here's dark green, brown, some lighter purple, light green, red, and we see that they always get added onto the end. We now also see a couple of colored circles emerging, the outlines. The red outline always points to the head, the yellow outline always points to the tail. We see that every time I add a new color, the tail moves up and up and up and up and up and up and up. So that's insertion at the tail. If I change this to insert at the head instead, then when I add the colors, we see that the new color always comes in at the head. And I made it this pretty little spiral to also sort of mimic what we had implemented earlier when we built the circular queue using an array. So here, the color gets inserted to the beginning. All the other colors appear to be shifting up, but we know that from the functions we just wrote, the insert at head and remove at tail, that nothing actually shifts. Nothing actually shifts, right? We're only updating these three pointers. There is no O of n shift going on. We don't even have to look at all of the other items. We don't care about all of the other items in the list. All we update is the pointer for the head or the tail and the pointers for the new guy, which means that this is always O of 1, and the shift of all the other items happening is just part of the visual here to accommodate them, because there really is no other way to represent it visually, right? Okay, so that's insertion at the head, that's insertion at the tail. Let's stick with tail for now, because tail I think is kind of the more, let's say, easy to visualize one. Inserting at the head and all that shifting is a little bit weird. So we'll insert at the tail, and we'll look at how to make this into a queue. So if we're inserting at the tail and removing at the head, it's now a queue. So what do we have to do to remove at the head first? So here we run into a little bit of a special case. If the node that we're trying to remove happens to be the very last one, then instead of updating any of the pointers or doing any of that stuff, all we have to do is set the head and the tail to null, and then the list is now empty because it can no longer access its head and tail. So the reason that this works, the reason that this if statement here passes, is because that if this is the only node in the entire list, then remember, as we initialized it here, the head and the tail were the same node. And if we insert it into an empty list, the head and the tail are the same node. And as we'll see, if you remove all the way down to the very last item, then it also becomes true that the head and the tail are the same node. You'll also want to think back to how we implemented the circular array, the queue with a circular array, and remember that to check if that was empty or full, we did a very similar thing. We checked if the head and the tail pointers were at the same spot and the spot was empty, then the list was empty. If the head and the tail pointers were at the same spot and that spot was full, then the list was full. Well, the empty check is basically the same for linked lists, but the full check is not the same because linked lists can never be full. Linked lists don't have a preset size. As you've probably noticed so far, as we've been adding items to the list, it's not like we run into any kind of index. So the only limitation for a linked list to how many items you can add is when your system runs out of memory to store them. Alright, let's move on to the removal part. So, handled the special case, let's look at what happens the rest of the time. So, the new head, let's imagine that we're removing, is it the only place I have this? Okay, lovely. Let's imagine that we're removing the head 2. What happens? Well, who becomes the new head? Obviously 0 does. And how did we know that? Well, it was 2's next node. So we know which node is going to become the new head by looking at 2's next link. So the head is now the next link of the old head. I stored it here as a temporary variable, but we could have just said head.next like this too. That would work perfectly fine as well. I'll keep the temporary variable just to be consistent with the next line. So the new head is now 0, and I also have to remember to remove this previous link, because if I keep this there, then I don't have null to the left of my 0, I have 2, and that's not correct. So I'm going to remove this previous link, and then this becomes the new head. But what I actually don't have to do is remove this link, the link from 2 to 0. That doesn't matter, because by establishing that null is now to the left of 0, so by establishing this, I've already removed 2 from the list. So even though 2 is out there in the ether floating around somewhere with a complete link to 0, it's now orphaned from the rest of the list. It's not connected to the head or the tail in any way. The only way that it was connected before was through that previous link. The only way that it was connected before that was it used to be the head, and it used to point to 0. It still does point to 0, but it's no longer the head, so we can't access it from there. So if you start at node 0 or you start at node 1, the head or the tail, you'll never be able to reach 2. It no longer has any connection to any of the other items in the list. So when we remove things from a linked list, we're actually not deleting them. We're just removing all of their connections to the rest of the list. So what happens to those items? Well, once they're orphaned, it's up to the garbage collector to figure out when they're no longer in use and then remove them. Otherwise, they just hang out in our system's memory until the program's done. And because of this functionality, this is one of the many reasons that linked lists aren't very performant. They leave behind a lot of this garbage, this cruft, that doesn't do anything and that needs to be kind of collected or picked up. Otherwise, it just clogs up the memory with all these orphaned nodes that don't do anything anymore. All right, so that's how to remove at the head. Let's see it in action. Let's go back to the display. I think it was the A key. All right, so the A key removes at the head. We're going to add some stuff to the tail. We'll add a few different colors in order, Okay, a bunch of different colors. Now, if I hit the A key, it should remove this head, the red color, and then this blue guy, the darker blue, should become the new head. There you go. It became the new head, and then everybody else scooted up, but remember, that's only part of the display. The rest of the list actually didn't change. It was only that head, and then the second node right after it that had any change done to them at all. And I can remove the head again and again and again and again, and this looks very much like the circular array functionality that we had earlier, because this is essentially already a queue, and a much easier implementation, obviously, than the one that we went with before. But also a lot less performant for reasons we'll look at later, and that we already discussed a little bit, the garbage issue. So this is always O of 1, which is great. Always O of 1. Likewise, removing at the tail, very similar. I won't even go into it in too much detail. Again, always O of 1. What do we have to do? Well, don't want to lose my copy pasta. All right. So what do we have to do if we are removing our tail here, if we're removing 1? And this should demonstrate to you that when you remove the tail, the head and the tail become the same again. If there are only 2 items in the list and you remove the tail, then the head and the tail are going to be the same item. So tail equals n dot previous. Remember, we're removing 1, the tail. So the new tail is this guy, n's previous. That's correct. Lovely. And then n dot previous dot next equals null. So 1's previous, which is 0, its next now points to null instead, so that now points to null. Now we no longer have a tail that's different. They're now both 0. And remember that this little bit here, the 1 pointing to null part, just floats around somewhere. It's orphaned from the list and no longer accessible. And there we go. We've removed from the tail instead. So let's run that and look at it in action. Again, I'll add a bunch of items. This is going to be the S key instead of the A key, so if I hit the S key, it will remove the tail. Add some more items, again remove the tail, whereas the removal of the head looks a bit different. So again, that's removing the tail versus removing the head. Okay, let's look at some of the more complicated cases then. We've looked at inserting at the head, we've looked at inserting at the tail, we've looked at removing the head, we've looked at removing the tail. Those are all O of 1, which makes linked lists seem like a very appealing data structure. Let's look at inserting into the middle, which is a place where linked lists are okay, but a little bit weak. So if we think back to arrays and array lists, inserting into the middle required us to first find the insertion spot, which we could do a little bit more efficiently with like a binary search or something, but for the most part we did it with like a simple O of n for loop. After we found the spot where we were supposed to insert into, then we had to shift all of the items over to the right beyond that, and then we could put it into the empty spot. That's how we had to insert into arrays and array lists. When we looked at stacks and queues, they didn't have a concept of inserting into the middle, so it wasn't really relevant to them. Okay, so we want to insert into the middle of a linked list. Let's add some more items to this one so that we make it more interesting. Let's add 4 and a 7 and an 8. So we'll assume that this one is sorted. Doesn't have to be sorted for us to want to insert at some index. And I'm not going to label the head or the tail anymore because I think it's pretty obvious. It's always the first and the last item, right? Okay, so if we want to insert at some index, let's say that I want to insert 2 at index 2. And if I mapped out my indexes, this one isn't an index, it's not really part of the list, it's just the imaginary null that's off to the side of the head. So this is 0, this is 1, this is 2, this is 3, this is 4. This is also not applicable. So I want to insert at index 2. Well, the first question you have to ask is, do we want to insert before or after? Because that determines whether or not we want to shift all the items from 4 and beyond to the right, or we want to shift all the items from 1 and beyond to the right. Either way is fine. In this case, I said inserts right after the given index. So let's actually keep this in order, and let's insert 2 at index 1 instead to make it more straightforward. So first of all, if the list is empty, it's very simple. We're just going to insert into the only available spot. It becomes both the head and the tail. Should be straightforward there. Otherwise, we have to loop through the linked list to find the index where we need to insert at, because you might have noticed that none of the nodes have tracked their index. We don't know what is at what index. And you might ask, well, why don't we? Why don't we keep track of which node is where? Why don't we add like an index functionality here? And you'll see that doing so actually destroys one of the only advantages to linked lists that we have, which is that insertion, even into the middle of the list, still happens in O of 1 time. So unlike our circular array, which was able to insert to the head and to the tail in O of 1, but couldn't insert into the middle, we didn't even implement that because it didn't make sense. If you tried to insert into the middle of a circular array, all those items to the right would still have to shift over. It would still incur O of n insertion time. Linked lists can actually do insertion and removal even in the middle in O of 1 time. But that doesn't include the search, as before. So this is due to the search. The insertion itself is O of 1. Alright, so let's do the search. How do we loop through, how do we traverse a linked list? So we start at the head. I labeled node curve or current as the head. I'm going to track the indexes that we visited as I go. And while the current node that I've run into is not null, I'm going to continue to move up. The I++ is to keep track of the indexes. but this step is actually the one that moves on to the next node. It looks a little bit recursive, right? It's saying current is its own next, right? It has a little bit of that self-dealing functionality to it that we saw in recursion. So it can be a little bit tricky to understand, but think about it. If current starts at the head, and then we go until it's no, and then we just take the next node to be the new current node, well then we'll just hop over. We'll start at 0, we'll go to 0's next, which is 1, we'll visited 1, we'll go to 1's next, which is 4, we'll go to 4's next, which is 7, we'll go to 7's next, which is 8, and then we'll go to 8's next, which is null, and then we're done. And that's how looping through a linked list works. You just visit them, typically using a while loop like this. You very rarely see any use of for loops in linked lists because we don't know how long they are. We don't know their endpoint. We could keep track of the size of the linked lists and add 1 to it every time we insert, subtract 1 every time we remove, and then structure this as a for loop instead. We could do that, but that's relatively uncommon. You don't generally see that approach because it just kind of doesn't make sense to do so. It's an extra overhead that doesn't really give you any advantage unless knowing the size is important to your application somehow. And the while loop is always the more expected, easier way to follow for traversing the linked list. Okay, so let's look at the actual payload of the function. Once we've reached that index that we're looking for, that I equals index, here's the part where we actually have to insert it. Now this is pretty complicated. It's a lot more complicated than our insertion at the tail and the head. Let's look at what it looks like without the special case first. Let's look at just these base 4 values that we have to update. And then we'll talk about the special case in a second, so I'm going to comment this out for now, we'll come back to it. So if I'm inserting 2, and I want to put it right here, so this is the new guy, it's 2, what has to happen? Which links have to be updated? Well, we see that 4's previous had to update to 2, 2's next had to update to 4, 1's next had to update to 2, and 2's previous had to update to 1. So altogether, 4 things had to change. Let's actually write this in before and after terms. So this is before, and here we will have after. Okay, so before, 4's previous was 1, now it's 2. Before, 1's next was 4, now it's 2. And of course 2 is brand new, so both of its links have to be freshly updated. 2's previous is 1, and 2's next is 4. So 4 things had to happen. The new nodes, previous and the next, are, remember this is if we are at index 2, this is 4. We're inserting an index 1, so this is 1 that we're at. So n.previous equals cur, that's 2's previous link, this one, equals 1. That's the node we're currently at. Remember, I equals index, node 1, node I, so it's index 1, also node 1. Probably shouldn't have named them numbers too, should have done letters or something, but whatever. Alright, so the node at index 1, that one becomes the new guy's previous. That's this part. The new guy's next is 1's next. So what was 1's next before? It was 4. So the new guy's next is now 4. That makes sense too because it got inserted between them. What's next? Well, the current index 1's next's previous. Remember I said that we would have to do this again when I covered the sentence example, and I said, what about this words, next words, previous words? Well, that's a little complicated. Okay, 1's next is 4. And 4's previous link, well, we know that no longer points to 1. It's got to update. It's going to point to 2 now. That's what this line's doing. It's saying 1's next, which is 4. Its previous link, that guy, is now pointing to the new guy too. So that sets this part. And then 1's next, this link here, points to the new guy, so 2. So altogether, those are pretty hard to conceptualize. Maybe watch that again if you didn't get it the first time, but there you go. We've established that connection. However, what happens if the index that you're trying to insert at is the tail? What if you end up trying to insert here at the at index 4, so at 8? Well, then this line here, cur.next.previous, 8's next is null, and if you try to access its previous, then because that's a null pointer exception. And that brings us to this slightly more complicated implementation here that you have to have. So if the node that you're trying to insert into is the tail, then you actually just want to insert at the tail. So that's the functionality that we already have. I was able to recycle it and bundle that all together. So maybe an easier way to rewrite this is also to have all of this stuff together like that. That would work too. That seems more straightforward to you. But if it's not the tail, then all of this wonderful stuff applies. And you'll notice that we don't encounter that problem if we're trying to insert at node 0, the head, because none of this stuff actually bumps into a null pointer in that case. The head's next is 1, it still has a previous, no null pointer exception there. The head's next is still n, no null pointer exception there. So it was only because I inserted after that I had to do this. Now if I inserted before instead of after the index, then it would be the other way around. I would have the problem at the head instead. So think about how it would change if you inserted before instead of after. Okay, hopefully that made sense, but there's one more thing to handle, which is what if we get to the end and we haven't run into the index yet, because in a linked list there's no guarantee. Let's say we're trying to insert at index 8. There's no guarantee that there's 8 items in this list. Well, at that point we could either fail or we could just insert on the end. So I've opted to just insert onto the tail. If we get to the end and we didn't reach the index we were looking for, then we just insert at the tail. Alright, so let's see what this looks like in action. Hopefully I didn't mess anything up playing with it there. So when you hit the spacebar, it's going to try to insert at index 5. Let's just hit the spacebar with nothing there, and it's going to insert a specific color. It's going to insert cyan. So if we hit the spacebar with nothing, then it's going to trigger this insert if empty, and there you go. If we hit the spacebar and there is not nothing, then we're going to move on to this functionality here. It's going to try to loop through them, it's going to try to find index 5, and it's going to fail, and it's just going to insert at the tail instead. So here we get a tail insertion, nothing special there. But let's insert a few more items, and now try inserting at index 5 again. So it should insert at 0, 1, 2, 3, 4, 5. It should insert right after this pink node that I'm currently hovering over. And there we go. It's inserted at index 5. If I remove the head, sorry, that was the tail. I remove the head a couple times, and again try to insert at 1, 2, 3, 4, 5. Again, it should insert, 0, 1, 2, 3, 4, 5. It should again try to insert right after this pink circle, and there you go. And if I hit the spacebar again, I'll just keep inserting them after that. If you hold the spacebar down, you can get the wonderful spiral, similar to the one that you had in the circular array. Okay, so that's inserting at a particular index, which will be of some use to you in the homework as well. And if you're watching this before the homework is due, the starter's already up. If you're watching this after, go ahead and look at the solution if you want to see how to insert after the currently selected node, where a right-click selects the node inside of this thing here. So a right-click should select that node, and then trying to click one of these guys above will insert the node after the one that's selected, or before the one that's selected, depending on which one you clicked. So that's actually going to be even easier than inserting at an index, because hint, hint, you don't have to search for the right index before. You already are at the node where you're supposed to be. All you have to do is handle the insertion, and then potentially the special case of the one you clicked being the very last one. Alright, that is inserting at a particular index. Now let's look at searching. Let's look at, I want to find which index a particular item is at. This is going to be where linked lists do the most poorly, and this is also why linked lists are not a very popular data structure, because this is what you need to do if you want to access arbitrary items in your list. So you want to see, for example, maybe this is a linked list of employee data. You want to see if some employee is in the list or not. Well, of course, you've got to loop through the whole list and try to find them. Now, even if your linked list is sorted, there really isn't a better way to do it than to start at the beginning and go through to the end, unless you implement a more advanced linked list, something like a skip list, which we're not going to look at. And because you've got to start at the head and move to the end, it's always O of n to search a linked list in that way, which is the only way to search a regular, not skip list or something. It's always O of n to find the item that you're looking for, and that's really slow. We can't use like a binary search, for example, unless, again, we add some extra functionality to it, and those are not without their own trade-offs, so don't think that that's like a free solution. So very slow to find a particular item and return its index, and that is most of our operations. In most applications, searching for an item, accessing an item, finding the location of an item, determining whether an item is in the list or not, those are the interactions that dominate the usage of the data structure. Insertion and deletion happens a lot less often than looking into the list. And that's why linked lists are generally a poor choice for most applications. Unless insertion and deletion dominates the usage, like almost every operation is either an insert or a delete. This is the case if you have something like a queue. So if you're actually using it like a queue, linked lists aren't a terrible choice. But otherwise, linked lists are usually uncommon. So you don't see them that much in production code bases compared to other data structures. So why do we even learn linked lists? First of all, they're a cool intro to other data structures in the future that are similar, have the same kind of reference structure where they're made of nodes and they point to others. That's a good starting point. But also because linked lists aren't very popular for interview questions, and therefore every graduate in computer science needs to know at least enough about them to get past those job interviews. Okay, so getting an index, pretty straightforward. It's the same kind of looping through the list that we saw earlier. We start at the head. While it's not null, we move on to the next one as we go. We're also tracking the index here so that we can return it. And then we've just got a simple check for equality. If the one that we're on is equal to the color that we're looking for, we're going to return the index. If we get to the end and we haven't found it yet, we're going to return -1. So nothing particularly unusual there. All right, the only other thing we have to look at, let's see, what else is there? One other thing before we part for the day. Ah, yes, we were just going to handle it conceptually. Okay, we handled the insertion at the head, we handled the insertion at the tail, and then we handled the insertion at a particular index. We handled the removing at the tail, we handled the removing at the head. So let's look at just conceptually without writing the function, because it's going to be part of the homework, although skip ahead to the solution if you're watching this after October, first week of October 2022 or so. All right, how would we find and remove some items? So let's say we want to remove node 4. Remove node 4 in the following list. And one of the things that you get to do in the homework is that you get to know the location of the node. You get to get the reference to the node without having to search through it. So this is kind of a good application for linked lists, because remember I mentioned that inserting is O of n. Removal is also O of n due to the search. The actual insertion and removal itself is O of 1. So I should really not be saying that it's O of n. I should really say that it's O of 1. In fact, if you look at like an online resource or something that'll tell you what's the big O performance of different data structures, they'll always tell you that the linked list insertion and removal is O of 1, because it's the finding the item that takes time. But in the example that you're given, in this example, you get the node from the left-click event that happens to it. It loops through all of the different, there we go, we loop through all of the different nodes, and then you've got the button that the node that you clicked on given to you already. So you already know that node 4 was clicked on in this example. Now, you will note that there is still this O of n loop in order to see if you clicked on any of them, but that's inevitable. There's no way to check on, did you click on any of the nodes in a list of n nodes without checking if you clicked on n nodes. It's always going to be O of n, regardless of your data structure. So alright, the node is known. We want to remove node 4 in the following list. Your nodes are colors, not numbers, but the principle is the same. What do we have to do in order to remove node 4? Well, we have to break this link, the link from 4 to 7, and break this link, the link from 4 to 2. We also have to update the link from 2. It now has to not point to 4, but point to 7. And we also have to update the link from 7, the previous one. It now has to point not to 4, but to 2 instead. So the resulting list will look a bit like this. Pretty easy to get this done. We will just remove that there. We end up with that. Pretty straightforward. So you'll notice that 2 links got deleted. Those were the links that 4 used to have. And then you'll also probably end up with somewhere floating off in space. Whoopsie. An orphaned 4 that just points to nothing. So when I said you've got to remove 4's next link and 4's previous link, well, you don't actually have to do anything to them. You just have to break the link from 2 to 4, update it to 7, and break the link from 7 to 2, update so 7's previous points to 2, and the job is done. So the only things that have to update for you to go from state 1 up here to state 2 is 4's previous's. Ooh, apostrophe S or apostrophe? Let's go with a single apostrophe. 4's previous next is now 7. And 7's previous is 4's previous is next. So 2's, 4's previous is 2. 2's next is now 7. And then 7, which is 4's next. 4's next's previous is now 2. So 4's next's, which is 7, its previous is now 2. So one more time, to remove 4, all we have to do is set 7's previous to 2 and 2's next to 7. If we think about what 2 is relative to 4, 2 is 4's previous, so 4's previous is next is now 7. But what is 7? Well, it's actually 4's next, and then 4's next, 7. Its previous, which should be 2, is now 4's old previous. So there's the logic. I'll let you figure out the code solution to it in the homework, or again, check out the solution if it's after the first week of October or so. And let's call that a wrap for today. That's your intro to linked lists. Hope you enjoyed it. I will see you next time for another exciting data structure with some algorithms.